Hello everyone, my name is Joy Okolo. I am a computer science student of McComish Department of Electrical Engineering and Computer Science at South Dakota State University. I am excited to share my work titled CLAMP, Client-Oriented Adaptive Model Pruning for Stragglers in Federated Learning, Enabled Mobile Edge Computing. I would like to use this time to acknowledge my PhD advisor and co-author on this work, Dr. Jun Huang. Without further ado, let's dive into it. This is the outline of this presentation, and I will be introducing the work, talk about the challenges, the current approaches that has been used in trying to solve this straggler problem in federated learning, talk about the research gaps, the CLAMP approach that we developed, talk about the experiments we did, the results we achieved, the contributions of this work, and the future work. Then I conclude. Introducing federated learning in mobile edge computing. One may ask, what is federated learning? This is a distributed machine learning approach where multiple devices collaboratively train a shared model without sharing raw data. So what happened is different devices train a model that is being sent to each of them from the server. They train this model locally with their local data. They do not send the raw data to the server. What this does is it preserves the privacy of the data of these clients, and only the model updates is being sent back to the server, which aggregates the model updates, come up with a new model, resends it back to the devices. The devices trains locally again and sends back to the server. This is how the round goes on and on until convergence is achieved. Mobile edge computing. Mobile edge computing is a paradigm that brings the computation closer. The computation comes closer to the data sources. And these are devices like your smartphones, IoT sensors, like the laptops we use, the everyday devices we use. So these devices, of course, suffers heterogeneity, which is the challenge. It suffers heterogeneity because the data in my cell phone differs from the data in another person's cell phone. Likewise, our laptops and smartwatches and the sensors and all of the IoTs and all. So because of this heterogeneity, we have the stragglers. These are the devices that are not quick, that we can call them slow devices. And this is where the question comes. What happens if you want to train all these devices you want all these devices to train a model, whereas we have devices with lesser computational power? What happens? How do we manage such system? So a straggler, of course, is a device that takes significantly longer to complete its training task. What this does is that it slows down the entire process and it makes the entire training round to be as fast as the slowest participant, because in this system, this server will have to wait for the different clients to submit their updated models so that it can aggregate them and update the central model. So because of that wait for the aggregation, the entire training round becomes as fast as the slowest participant. There are works that have gone into this straggler challenge to see how to solve it. Some researchers worked on excluding the stragglers, which is the exclusion method. So what happens is they use the updates that come from the fast devices, possibly send a timer. Once it's at this time, the devices that are able to converge, that are able to come up with their model update will submit it for aggregation. They don't necessarily have to wait for the slow devices. What does this do? What does this do? Sorry. It prioritizes speed over fairness. And for the static partial training, this set of researchers sends a reduced layer of the model to all the devices. Both the slow devices and the fast devices trains a subset of this model. What happens here is that the fast devices are not completely utilized because the fast devices can actually do more. But because we are trying to favor the slow devices, these researchers tends to reduce the layers of the model they send to all of these clients. There we have the research gap. The existing approaches uses the static method or the exclusive method, which leaves us with system that does not have the adaptive nature, that does not adapt to real-time condition. And this leaves us to the need for dynamic adaptation. We need a system that has this real-time responsiveness, that understands the condition of each client at every round to adjust accordingly. It maintains inclusivity and there will be no device exclusion. And this is what our clamp provides. Let's look at clamp. This is a dynamic client-oriented approach. It adapts to real-time device conditions. For instance, a device might start off as a fast device. In the course of the rounds, might lose bandwidth. It might lose its battery life. What happens? You notice that this device becomes a slow device. How do you handle this change in conditions of these devices? We work with real-time condition. So what happens at first is that all the devices trace the full model. We set a time threshold. Then we calculate the elapsed time of each device per round. If the time is higher than the upper threshold, that means that device is a straggler and we reduce the layers. Let's look at the next slide. So in federated learning setup, we have the central server, like I already explained, and this central server coordinates the n number of distributed clients. We have the global model, which has the number of ordered layers, which is the maximum number of ordered layers in the central model. For each round, the server selects a subset of clients to participate, and after the participation, we calculate the completion time of each client, and we calculate it by calculating the computational time plus the communication time. That is how we get the client completion time. And when we get this time, we compare them with the stragglers. How do we know that a device is a straggler? It is a straggler if its completion time exceeds the median. For each round, we calculate the median time of each device. So if their completion time is higher than the median time in that round, then it's a straggler. If not, then it is not a straggler. We also introduced the slow device inclusion ratio. What does this do? For each round, we count how many slow devices that we are able to participate, and the intersection of the participating client and the set of these slow devices, we divide it by the total number of slow devices in the system. That is how we get the SDIR, and more SDIR, the higher the SDIR, the more the fairer the participation of slow devices. And our clamp was able to maintain accuracy while improving SDIR. Then how does our system adapt to changing capabilities of these devices? The first thing we set is the lower threshold and the upper threshold. We set the lower threshold to be the 90% of the median runtime, and we set the upper threshold to be 110% of the median runtime. So if the elapsed time of that device is less than the lower threshold, that means that device is actually a fast device, and we increase the layer by 1. And while increasing it, we must not exceed the maximum number of layer, which is the capital D. But if the elapsed time of that device is greater than the upper threshold, what it means is that that device is actually a slow device, it's a straggler, and we have to reduce the layer by 1. And while reducing, we don't go less than 1 layer. Then the next thing is to find the common depth after local training. We find the common depth. What is this common depth? It is the smallest number of layers trained by any client participating in that round. And this is the standard federated learning averages. It's also used by Fed average. So after getting the common depth, the server goes ahead to aggregate this common depth. After aggregating the common depth of the smallest number of layers that were trained, it also handles the deep layers. What happens to the deeper layers is that the server keeps the weight and wait until more client trains them. Then it updates the deeper layers. This is our experimental setup. We trained this model. We used different data sets. We used MNIST, Fashion MNIST, and we used Cypher 10. And we tested it on 3 different baselines, using it to do a comparative analysis with our work. We used Fed average, Fed PMT, and Fed drop. And we worked with this setup where the number of clients is 100. It selects 10 per round. And we also have this heterogeneity in the system. And we have our straggler tolerance to be 1.5. After experiments, we came up with this result for the MNIST dataset. Accuracy for clamp was 97.82%, SDIR of 20.3. It converged very, very early at 76 rounds and at time 776.8 seconds. For Fashion MNIST, our clamp performed well with accuracy of 87.49%, SDIR of 41.2%, 95 rounds, and 7,010.4 seconds. And it came out with the lowest computational cost for Fashion MNIST when compared with Fed average, Fed PMT, and Fed drop. Then for Cypher 10, accuracy of 85.10, SDIR of 1.9, 236 rounds for convergence, 61,110 seconds, and it has higher cost. On complex tasks, because Cypher 10 is a more complex data set. Then we have our average performance table where we compared Fed average, Fed PMT, Fed drop, and clamp. Clamp outperformed Fed drop and Fed PMT in accuracy, outperformed Fed average and Fed PMT in SDIR, outperformed Fed PMT and Fed drop in rounds, and outperformed Fed PMT and Fed drop in average time. The key contributions we have here is that we developed the first client-oriented dynamic layer allocation framework using real-time feedback. We also defined the SDIR metrics, which is used to check the fairness in the system, how slow devices were able to participate. We also eliminated the fixed depth truncation bias, which we saw in the static PMT methods. We are able to achieve competitive accuracy with significantly reduced training time. The future work we are looking at for this work is the mask-aware layer-wise aggregation. In this case, we are looking at not using the common depth for the aggregation. What if we utilize the deeper updates as well, as we may need those results? Then adaptive threshold when it comes to setting our upper bound and lower bound time. Then the real world deployment is also a future work we are looking at. Conclusively, CLAMP solves the straggler problem in federated learning by dynamically adjusting how each device trains based on real-time device, and we're able to make good progress. It maintained competitive accuracy while significantly improving fairness. Thank you.